Subdivide magnesium nitrate hexahydrate into vial inside the glove box. TGA and DSC devices are located at RA 202. Open the nitrogen gas valve. Switch on the TGA device. You can tell that the device is powered on by the green light at the bottom. Run the TA Instrument Explorer program and set the specified parameters. Set the sample name, pan type, and storage location. Click Procedure and press Editor button at the Method part to set the specific temperature conditions. Set initial and equilibrium temperature as 30 degrees Celsius, heating rate to 1 degree Celsius per minute, and final temperature to 800 degrees Celsius. Enter operator part in the notes section, and finally set gas type as nitrogen. To calibrate the scale, lift an empty pan and press the tar button. Hook will engage automatically. If not, carefully place the pan on the wire. Afterward, the pan is suspended and the furnace ascends. The furnace descends automatically when the calibration is done. Head to the location where scale is located and measure the weight of sample. Tare the pan. Measure the weight of the sample. Place the pan on the TGA device. Press Sample button. Pan is suspended automatically. Holder moves automatically, and the furnace ascends. Click the arrow in front of the dot spot to run the program. After the measurement, furnace will descend automatically. At the same time, file will also be saved at the storage location. After the measurement, switch off the device. Click TA Universal Analysis and open the file at the storage location. Through TGA analysis, we identified the thermal decomposition behavior of hexahydrated magnesium nitrate. Around 150 degrees Celsius, magnesium nitrate dihydrate was formed. At approximately 290 degrees Celsius, anhydrous magnesium nitrate was produced. Further decomposition into magnesium oxide occurred at around 430 degrees Celsius. Based on this result, we determined the optimal temperature range to isolate anhydrous magnesium nitrate without further decomposition. Tare the T0 pan before measurement. Weight the sample on the T0 pan. Take out T0 pan flat die and lower die from bottom of the desk. Insert both flat die and lower die into the presser and place T0 pan with lid closed. Afterward, move the handle to press T0 pan. Verify that the lid of the T0 pan is well closed. Open the valve of nitrogen gas. Turn on the chiller. Switch on the DSC device by pressing button. You can see the DSC monitor after turning on the device. Press the control button on the DSC monitor. Select Go to standby temperature and press Apply button. You will be able to adjust the temperature up to 40 degrees Celsius. Temperature has been adjusted to standby temperature. Set lid, open on the DSC monitor, and press apply button to open up the lid of DSC device. Place the zero pan next to the reference sample. Set lid, closing on the DSC monitor, and press apply button to close the lid of DSC device. Click DSC software icon at the computer. Set sample name, sample weight, storage location in the summary part. Set pan type as platinum. Set specific parameters at the procedure part. Enter operator at the notes part and double-click the check, and the check will turn out to be dot spot. Press the play button to start the measurement. After the measurement, turn off the chiller. Press go to standby temperature, and press apply button to descend the temperature down to 40 degrees Celsius. Set lid, open, press apply button to open up the DSC's lid and remove the sample. Set lid, close, press apply button to close the DSC's lid. Set shutdown, and press apply button to turn off the device. Close the nitrogen gas valve, and remove the remaining nitrogen gas. By using TGA Universal Analysis Program, you can check out the measured data. To support the TGA results, DSC analysis was also conducted. A peak around 100 degrees Celsius indicated water evaporation. Another peak at 270 degrees Celsius was attributed to the thermal decomposition of hydrated magnesium nitrate into anhydrous magnesium nitrate. This confirmed, in agreement with the TGA data, that decomposition occurs at around 290 degrees Celsius. Since further decomposition into magnesium oxide was observed near 490 degrees Celsius, the drying temperature was set to 290 degrees Celsius to obtain anhydrous magnesium nitrate for use as an additive. This is the configuration of lithium symmetric coin cell. Assembly of lithium symmetric cell in the glove box to proceed critical current density test. Next, electrolytes are prepared using hydrated magnesium nitrate, anhydrous magnesium nitrate, and a base composition without any additives. The prepared electrolytes are then introduced into lithium symmetric cell. The assembly of lithium symmetric cell is completed by applying pressure using a clamper. Using TGA and DSC analysis, we identified the thermal decomposition temperature of hydrated magnesium nitrate and successfully obtained anhydrous magnesium nitrate by drying at the appropriate temperature. In typical coin cells, a base electrolyte consisting of EC, MP, and FEC is commonly used, contributing to SEI stabilization, improved lithium-ion conductivity, and fluorinated interphase formation, respectively. We further introduced anhydrous magnesium nitrate to this formulation to promote the formation of an inorganic-rich SEI layer, aiming to enhance cycle life. CCD tests showed that cells with hydrated magnesium nitrate suffered rapid degradation due to moisture, whereas cells with anhydrous magnesium nitrate exhibited lower overpotentials and significantly longer lifetimes compared to the baseline. These results demonstrate that anhydrous magnesium nitrate helps form a robust inorganic SEI, positively impacting cycling stability.